Aluminum is one of the most versatile metals in the world. Not only is it malleable as paper, but also as tough as steel. But have you ever wondered how a huge block of solid aluminum gets transformed into a paper-thin sheet of foil? Let's find out how millions of tons of aluminum is processed to make this paper-thin sheet of aluminum foil found in your kitchen cabinet. Aluminum foil was invented by a Swiss company in 1911 and was originally used to wrap its popular candy bar called Toblerone. With time, it found its way all the way to food counters. This was primarily because it was discovered that aluminum had unique barrier properties that completely block light, heat, and moisture. Up until the 18th century, several scientists tried to isolate aluminum, but were unsuccessful due to the challenging nature of the extraction process. When someone finally did succeed, they couldn't manage anything more than a little amount of aluminum powder. This meant that pure aluminum was a rarity, and the process for obtaining it was so complicated that it made it more valuable than even gold. The breakthrough in aluminum production came with the discovery of electrolytic reduction. But hey, we're getting ahead of ourselves here. Why not start at the beginning? The primary raw material used in the production of aluminum is bauxite, which is a mineral rich in aluminum oxide. Although clay also contains aluminum, it is far more economical, quick, and easy to obtain from bauxite, making it the primary ore of aluminum. Bauxite is typically mined in open-pit mines and then transported to refineries for processing. These mines are primarily located in tropical regions of the world. In fact, one of the largest bauxite mines in the world is located in Australia. You'd be surprised to know that this mine, called the Weipa mine, is responsible for producing 30 million tons of bauxite every year. Once the bauxite has been obtained from the Earth's crust, the next step is to refine it. The refining process involves several steps. First, the bauxite ore is mechanically crushed. Then, the crushed ore is mixed with caustic soda and processed in a grinding mill to produce a slurry, a watery suspension containing very fine particles of ore. The slurry is pumped into a digester, a tank that functions like a pressure cooker. The slurry is heated to 230 to 520 degrees Fahrenheit, 110 to 207 degrees Celsius, under a pressure of 50 pounds per inch squared, 340 kPa. These conditions are maintained for a time ranging from half an hour to several hours. Additional caustic soda may be added to ensure that all aluminum-containing compounds are dissolved. The hot slurry, which is now a sodium aluminate solution, passes through a series of flash tanks that reduce the pressure and recover heat that can be reused in the refining process. The slurry is pumped into a settling tank. As the slurry rests in the tank, impurities that will not dissolve in the caustic soda settle to the bottom of the vessel. The residue, called red mud, that accumulates in the bottom of the tank consists of fine sand, iron oxide, and oxides of trace elements like titanium. After the impurities have settled out, the remaining liquid, which looks somewhat like coffee, is pumped through a series of cloth filters. Any fine particles of impurities that remain in the solution are trapped by the filters. This material is washed to recover alumina and caustic soda that can be reused. The filtered liquid is pumped through a series of 6-story tall precipitation tanks. Seed crystals of alumina hydrate, alumina bonded to water molecules, are added through the top of each tank. The seed crystals grow as they settle through the liquid, and dissolved alumina attaches to them. The crystals precipitate and are removed. After washing, they are transferred to a kiln for calcining, a process that involves heating to release the water molecules that are chemically bonded to the alumina molecules. A screw conveyor moves a continuous stream of crystals into a rotating cylindrical kiln that is tilted to allow gravity to move the material through it. A temperature of 2,000 degrees Fahrenheit, 1,100 degrees Celsius, drives off the water molecules, leaving anhydrous, waterless alumina crystals. After leaving the kiln, the crystals pass through a cooler. To obtain pure aluminum, the bond between aluminum and oxygen in alumina or aluminum oxide must be broken. This is done through the electrolytic reduction of alumina into aluminum metal. This process, called smelting, takes place in a steel vat called a reduction pot. The bottom of the pot is lined with carbon, which acts as one electrode, conductor of electric current, of the system. The opposite electrodes consist of a set of carbon rods suspended above the pot. They are lowered into an electrolyte solution and held about 1.5 inches (3.8 centimeters) above the surface of the molten aluminum that accumulates on the floor of the pot. Reduction pots are arranged in rows, pot lines consisting of 50 to 200 pots that are connected in series to form an electric circuit. Each pot line can produce 66,000 to 110,000 tons, 60,000 to 100,000 metric tons of aluminum per year. Within the reduction pot, alumina crystals are dissolved into molten cryolite at a temperature of 1760 to 1780 degrees Fahrenheit, 960 to 970 degrees Celsius, to form an electrolyte solution that will conduct electricity from the carbon rods to the carbon-lined bed of the pot. Next, an electric current is run through the cryolite, causing a crust to form over the top of the alumina melt. When additional alumina is periodically stirred into the mixture, this crust is broken and stirred in as well. As the alumina dissolves, it electrolytically decomposes to produce a layer of pure, molten aluminum on the bottom of the smelting cell. The oxygen that is released is attracted to the carbon rods and escapes in the form of carbon dioxide. Still in molten form, the purified aluminum is drawn from the smelting cells, transferred into crucibles, and emptied into furnaces. At this stage, other elements can be added to produce aluminum alloys, with characteristics appropriate to the end product, though foil is generally made from 99.8 or 99.9% pure aluminum. This liquid is then poured into direct chill casting devices, where it cools into large slabs called ingots or re-roll stock. Once the aluminum ingots are cast, they undergo a series of mechanical processing steps to reduce their thickness and produce aluminum sheets. First, the aluminum ingots are heated and then pass through a series of rolling mills, which gradually reduce the thickness of the metal. This process, called hot rolling, can be repeated multiple times, depending on the desired thickness and properties of the final foil. After hot rolling, the aluminum sheet is further processed through cold rolling. This involves passing the sheet through a series of rollers at room temperature to achieve the desired thickness and surface finish. Cold rolling also increases the tensile strength and hardness of the aluminum. Between cold rolling passes, the aluminum sheet may be subjected to an annealing process, which involves heating the sheet to soften it and improve its formability. Annealing also helps relieve stresses introduced during cold rolling. The cold-rolled aluminum sheet is now ready for the specific process of turning it into aluminum foil. The foil rolling process is characterized by its precision and focus on achieving the desired thickness, surface finish, and properties. The cold-rolled sheet is passed through a series of foil rolling mills, which are specifically designed for producing thin aluminum foil. These rolling mills can consist of multiple rolls that gradually reduce the thickness of the sheet. To ensure a uniform thickness and smooth surface finish, the foil may undergo tension leveling, which involves stretching it over a series of rollers. During the rolling process, the foil is coated with a thin layer of oil or lubricant to reduce friction and prevent sticking to the rolls. Intermediate annealing may be required to further soften the foil and maintain its ductility. This allows for additional reduction in the thickness. After achieving the desired thickness, the aluminum foil undergoes final annealing and finishing processes to enhance its properties and ensure consistent quality. The foil is heat-treated in a controlled environment to relieve any residual stresses, improve its flexibility, and optimize its mechanical properties. The wide foil sheet is then cut into narrower rolls, which are the standard commercial sizes for aluminum foil. It should be kept in mind that throughout the production process, the foil is subjected to rigorous quality control checks to ensure that it meets the required specifications regarding thickness, tensile strength, and surface finish. Thickness is determined by weighing a sample and measuring its area, and then dividing the weight by the product of the area times the alloy density. Tension testing of foil must be carefully controlled because test results can be affected by rough edges and the presence of small defects, as well as other variables. The sample is placed in a grip and a tensile, or pulling force is applied until fracture of the sample occurs. The force or strength required to break the sample is measured. Once the aluminum foil has been produced, it is wound onto large rolls and cut into various standard-sized rolls or sheets, depending on customer requirements. The finished aluminum foil is packaged and labeled for distribution to manufacturers, retailers, and other end users. Aluminum is highly recyclable, and the production of aluminum foil benefits from the recycling of scrap aluminum. Recycling involves melting down used aluminum products and reprocessing them to create new aluminum products, including foil. The recycling process is energy efficient and helps reduce the environmental impact of aluminum production. That was all about how aluminum foil is made. We bet you didn't know so much goes behind the scenes of producing such a seemingly simple item. You know what else takes surprisingly long to make? Beer. And here's how it's done.